We're ready for the second part of the October 2022 paper from Physics Edexcel International A-Level, Unit 5. The topics are thermodynamics, radiation, oscillations, and cosmology. So the first video we did, we went through questions 1 to 15, and now we're going to try and do questions 16 to 20 in the second of the YouTube videos. Okay, so once again, please remember to like, share, and subscribe so we get lots of people watching our videos to make them really useful. We want to go viral one day. Anyway, I hope you find them useful. So, here we have question 16. Gliese, how you pronounce it, I don't know, 876, is a main sequence star in the constellation Aquarius. So this is just information, background information. The graph shows how the intensity, I, of radiation emitted from the star depends upon its frequency. So here you have the peak frequency. The peak frequency is normally given in wavelength, lambda max. So if you know the frequency max, you can work out the lambda max by use of C equals F lambda. Then you can use Wien's law, which is on your formula sheet, and they're giving you what the constant is. So lambda max times the temperature gives you a constant, always, for stars. Okay? So you can find this formula on the back of your exam, and then what you've got to do is show that the surface temperature, T, is about 3000 Kelvin. So we're going to try to do this. So the first thing we want to do is we get the value from the peak as being 3.2 times 10 to the 14 Hertz. 1 mark for getting it from the graph correctly. So basically, they want to know, do you understand what to do when you get a graph like this? In other words, have you revised? Well, if you have revised, you should be able to work out that they just change the wavelength to frequency. Normally, it's given as wavelength. Okay? So lambda max equals C over frequency max from the equation V equals C equals F lambda. So we know C is 3 times 10 to the 8. We know frequency is read off the graph as 3.2 times 10 to the 14. And we get a value of the wavelength, maximum wavelength, to be 9.38. So once we know that, we can put it into this equation. So there's the full equation from the back. There's the constant value. Yeah. So now you want to work out temperature. So you divide this constant by the wavelength that we just calculated, and you come up to 3090 Kelvin, which is approximately equal to 3000 Kelvin. So always make sure you go to the extra step to show that it is about 3000 Kelvin, because that's what they've asked you to do. There, the 4 ticks represent what the mark scheme is giving for this question. Okay, first half of question 16 done. So I'm just getting my notes in order. The ones that we finished with, make sure they're in the right place. So for part B, as a red dwarf star, the luminosity of this star should be less than 10% of the luminosity of the sun. By saying that it's a red dwarf star means it's small and therefore not very hot, and red, the color of a star, tells us the temperature. Once we know the luminosity, once we know the temperature, we can work out the luminosity if we know sigma, which is a constant given to you from the Stefan-Boltzmann law. So it's in the data sheet. The area of the star, which is a small star, so they'll give you the information to be able to work out the area. Well, they've given us the radius of the star. Once you know the radius, you can work out the surface area of the star as 4 pi r squared. So you can work out the area. This is data sheet. We just worked out the temperature from the last part. So we can then work out the luminosity. And we've been given the luminosity of the sun, and we want to work out, is the luminosity of this star less than 10% of the luminosity given for the sun. Okay, so we got the luminosity of the sun already. So you put the numbers in this equation. This is given to you on the data sheet. Okay, the area I worked out here, 4 pi r squared from the r they've given us, and I make it to be 8.63 times 10 to the 7, and that will be meters squared, and that's the area of a sphere. Then we can work out the luminosity for this star I just abbreviated to G because we got this one as the sun, S. Okay. So once you do that, this is the constant given to you. This is 4 pi r squared, which is this value. So this, I haven't put the answer in. The answer could have been put in. And I've used the accurate value. Okay. The mark scheme uses a value of 3,100. Okay. So why did they use that when the most of the data we've been given is 3 significant figures? Even in the first part of the question, I suppose here we only know to 2 significant figures. So they're assuming that brings us down in terms of accuracy. Okay. Anyway, I use the accurate value that was in from the part 1, 3090 Kelvin, and there isn't much difference in the final answer between using 3090 and 3100. So you get the luminosity of this star as 4.52 times 10 to 24 watts compared to our sun, which is 100 times more power, roughly. It's 4.52, 3.83, 2 extra powers of 10, 26 compared to 24. So if you actually divide those two numbers, you get 0.012, which is about 1.2%, which is way less than 10% of the sun's luminosity. Because a red dwarf star is red, so it's not hot. It's a dwarf, which is probably why it's not hot. So it's not very large, so it doesn't get to high enough pressures and temperatures to burn very quickly. Okay, so here I put what difference does it make to the value if you work out temperature to the power of 4. If you use the mark scheme value, you get 9.2. If you use my value, you get 9.1. So it doesn't really make much difference anyway, since it's way below 10%. So that's question 16 finished. Question 17 is also on astrophysics, or cosmology as they call it. The dwarf planet Ceres is the largest object in the asteroid belt. So the M for Ceres is 9.38 times 10 to the 20 kilograms, so that's the mass. Ceres has a circular orbit of 4.14 times 10 to the 11, so that's the orbital radius, around the Sun. Show that the gravitational force exerted. So the gravitational force exerted is given on the formula sheet as F equals gmm over r squared, where big M is the mass of the Sun, and little m is the mass of Ceres. So we know the two masses, G is a constant, and R is this. So we know all the values, you just plug in the numbers, and hey presto, you get your 2 marks, and it comes to 7.26, which is about 7.7 times 10 to the 17 newtons. Okay, so nice, easy 2 marks. Then it wants you to determine the time in years for Ceres to make one complete orbit about the Sun. So, circular motion. This is circular motion. So we know the force that we just calculated must be equal to mr omega squared, where we know that omega equals 2 pi over t. So this is how I did it. I replaced omega squared with 2 pi over t and squared it, and I came out with this equation. I'm not sure whether I should have done that or not. I'll show you the mark scheme how they did it. They worked out omega and then put in omega squared, which may be a quicker way of doing it. But whichever way you do it, so they worked out 2 pi over t, yeah, and did it their way. So I did it this way. What are we trying to find out? We want to find out t. So I've made t the subject of the formula, which if you can do the algebra, you'll see is 4 pi squared mr divided by f. So basically the t squared and the f change sides. Put the numbers in. Take out, square root it, or square root of 4 pi squared goes back to 2 pi. So it saves me doing that calculation. Put the values in, I get 1.45 times 10 to the 8. Then we know that 1 year in seconds is that, so we want it in years, so we've got to change that from seconds into years. So to do that, you divide by the number they've given you, and you'll get 4.61 years, which is approximately 4.6 years. So we don't want very large number of significant figures. So again, I'm giving these values to two significant figures. I'll just show you how they did it. Question 17. So they did, I think theirs is quicker. That's how they did it. So you can stop and do it their way, and so you can either do it, there's another method as well, you could work out the velocity and do mv squared over r. So there's different ways of doing it. I just made an algebraic expression which mixed the omega with the t, and I replaced the omega with t. Okay, so there are many ways to solve these problems. As long as you've got the problem solving skills, you do want to find the quickest route, obviously. And I'm not under time pressure when I'm doing these, so I might not have done it the quickest way possible. So 17 continues with the part B. Now it's talking about Mercury, the smallest planet in our system. Well, we're at Pluto. Pluto has now been excluded as a planet. Poor old Pluto. Gravitational field strength, G of Mercury, M for Mercury, at the surface is 3.7 newtons per kilogram. That's the gravity of Mercury. It is claimed that the gravitational field strength of the surface of Ceres, the one we just looked at, is less than 5% of the gravitational field strength of Mercury. Evaluate whether this is accurate. Evaluate means put values to it. Okay, so here they've given us the radius of Ceres is 750. This time they're using one of the other equations from your equation sheet. I think they've almost used every single equation in this exam. I'll show you afterwards. So G is 6.67, we used it before, times 10 to the minus 11. 9.38 is the value of the mass, which we were given before in the beginning of question 17. The mass is given there. And divided by the radius of Ceres, don't forget to change that into meters. So there's times 10 to the 3, and then that's squared. Okay? So once you square it, you come up with a very small value of 0.283. Just make sure I got that right compared to the examiners. Yes. Well, that is 0.283 out of 3.7. It's only 7.7%, roughly speaking, two significant figures again, which is greater than 5%. So the claim is inaccurate, okay, because it said it's less than 5%. Well, it's 7.7%, which is greater than 5%. So claim is inaccurate. So even this last bit, so claim is inaccurate, don't leave it to their imagination. Make sure you drive your point home to make sure they don't drop a mark. I've seen examiners' marks for my students, and they can be quite fussy about dropping marks for students who think, well, that's obvious, they should know that. Well, it's not for the examiners to decide whether you think it's obvious or not, or it's not for you to decide. They will take it off and you will be sorry at the end of the day. So, in 1935, question 18, the Curies, were awarded the Nobel Prize for discovery of artificial radioactivity, So I thought it was Marie Curie. So who are these? Anyway, they were bombarded an aluminium sheet, there it is, with alpha particles to produce a radioactive isotope of phosphorus, phosphorus 30, as in the nuclear equation shown below. And they're giving you an X element, an X particle, and they want you to identify what it is. Well, if it's got a mass of 1 and it's neutral, so remember the top numbers are mass and the bottom numbers are charge. So this particle has no charge and atomic mass units. These are atomic mass units. So it's basically the mass to one integer. So identified as a neutron, 1 mark. They then given you the exact masses in electron volt units, giga electron volt units. The c squared just indicates that when you're working out m using E equals mc squared, it's E over c squared. So they're showing that you've divided the energy by c squared and you've given it in the electron volt equivalent of the energy. Remember, mass is just a form of energy in physics, in nuclear physics. So they've given you all the masses, so the X is mass, alpha particles mass, and the aluminium mass and the phosphorus mass. So the mass afterwards adds up to 28.8602 mass units. Don't worry about the units. And the mass before, which was the aluminium and the alpha. So the aluminium and the alpha is before. So once you got the aluminium, you add a 25.133 to 3.7. So these two is on the left-hand side of the equation, and this is after on the right-hand side of the equation. So this is the left-hand side and right-hand side, and you'll notice that the left-hand side is the fourth decimal place is 5 bigger than the left-hand side. So 1, 2, 3. Oh, I put 1 too many. So that comes out. I think I've done it right. I just put too many. Is that right? 1, 2, 3. 1, 2. No, I was right. 1, 2, 3 zeros, and then a 5. So the difference between them is that many units. Okay, it's a decrease in mass. So if you've decreased the mass, it means, sorry, you're not seeing what I'm doing. If you decrease the mass, this minus that is 0.000, so 3 zeros, and then a 5. Okay. If you decrease the mass, it means you've made something, you've released some of the mass. You've released the mass into energy. So energy has been released in this process. Okay. So how do you work it out? Well, that's 5 times 10 to the 5 electron volts, because that's giga 10 to the 9, and this has, you've got to remove some of the things. Anyway, it comes out to that. So once we know that the giga electron volts, or the value given in electron volts, is that, multiplied by the conversion rate, which is 1.6 times 10 to the minus 19, and you get the energy in joules. So always, to change into joules, you multiply by the electron volt value by 1.6 times 10 to the minus 19. Remember, it comes from charge times voltage. Okay, so this is the value of the voltage. Like, it's like 5 times 10 to the 5 volts of energy that is given to an electron. So you can work it out in joules, which comes to 8.0 times 10 to the minus 14 joules for question 18. That's question 18, first part. Question 18, second part. The radioactive phosphorus was one of the first artificially produced isotopes to be used in the diagnosis of cancer tumors. The isotope P32 is injected into a person and collects in the tumor. Radiation is detected outside the person's body through the detector. Okay. Now, we know that P is a positron emitter. Okay. P is a positron emitter. Well, if it's a positron emitter, so the next thing that it will do, it will posit P30. If you want to write a nuclear equation for it, it will give off beta plus, which has 0 mass, but plus 1 charge, and this will be 15. So you could work out what it becomes, element X. Now, that's not what they're asking, but just so you have a little bit of understanding. Now, this positron emission has a half-life of about 15 days. So the half-life is about 15 days. So is that a long time to have it in your body? Well, I wouldn't like to have something radioactive in my body. But anyway, they use it for this purpose, to diagnose cancer tumors. So explain why it is suitable for this procedure. So P32, because it emits positrons, which will annihilate nearby electrons, yeah? They will automatically annihilate electrons in their path. They will produce, each time that happens, they will produce gamma radiation, okay? Which can then penetrate through the body to be detected. So obviously the positrons can't get through the body, they'll be absorbed, but the creation of the radiation through the annihilation of the positron, beta plus, with electrons, creates the gamma rays, which can then be detected outside the person's body. So that, from that point of view, it makes it suitable. And the half-life is long enough to be able to monitor the tumor, but short enough to avoid a large radiation dose. That's what you have to say. Okay? Now, again, I ask, would 15 days of radiation be too much? We don't know, because we don't know what the dosage is. In other words, how many particles do they need to put in there to make it detectable? It's a question worth asking. Medically, you have to approve any treatment they give you. It's called informed consent. It's the patient's right to agree to a treatment. Question 19. 2 questions to go. A can of spray paint. Yeah? Here's the can of spray paint. At first I thought it looked a bit like a microscope. Needs to be shaken before being used. Probably because you want to make sure that the paint is all evenly spread out in the liquid, whatever is holding it. The diagram shows a machine designed to shake a can of spray paint. Okay, so the bracket oscillates. So the bracket here is shaking, oscillates vertically up and down with simple harmonic motion. So basically this question is about simple harmonic motion. State the conditions necessary for any object to move with simple harmonic motion. Well, when an object is displaced, you know that there must be a restoring force, a restoring resultant force that is proportional to the displacement. So if you displace to the left, from the left of the equilibrium position, that's 1 point you get for the net. And the force will always act towards the equilibrium position. Yes? So if you move it to the left, the force will be to the right. If you move it to the right, the force will be to the left. Or, as you could clarify that, is in the opposite direction of the displacement. Okay? Acceleration-wise, we put that as a equals minus omega squared x. So it creates that oscillation. And F equals ma. So F equals minus m omega squared x. So that's where it comes from mathematically. Okay, part B. When the bracket is oscillating, the distance between the highest and lowest positions of the bracket, so when it goes top and bottom, is 8 centimeters. That means the amplitude is half of the distance between the top and the bottom, because the amplitude is a distance from the equilibrium. So you need to measure the displacement from the equilibrium position, which will be in the center. Okay, so it's from the highest to the lowest means above the equilibrium and below the equilibrium. The bracket oscillates, completes 270 oscillations per minute. So you can work out the frequency as 270 divided by 60 to get it into seconds. So once you do that, you'll see that you'll get 4.5. So the automatically getting the frequency allows you to get 4.5, allows you to work out the period. So what? Because they want you to sketch a graph on the axis opposite to show how the velocity of the bracket, which is oscillating the can, depends upon time. Now, they want you to know which equation it is. You should include velocity and time values on the graph. So the graph looks like that. Okay, I'm going to show you this with the graph present. Okay, hope that makes sense. So I put it on the same page, effectively. So we worked out the frequency. We can work out the period. So I've then drawn my graph starting as a minus value. Okay, and therefore the complete oscillation from the trough to the maximum and the minimum. So the amplitude would be here. Yeah, the amplitude would be, what are they saying? The amplitude is 8 centimeters. Well, we're not drawing the amplitude in this graph because the amplitude is a velocity. And the velocity is given by A omega sine omega t, which is on your formula sheet. Okay? A omega sine omega t. So here are the equations for oscillations. It's question 19b. Yeah? So we can use this, and remember omega is 2 pi f. We've already used this, so they're putting quite a lot of the equations in there, and they've just asked us about the restoring force, defining simple harmonic motion. So question 19 is all about simple harmonic motion, uses all the equations almost. So once we got that, the maximum velocity will be when sine omega t is 1. A is the amplitude, okay? The amplitude is given here. So we know the amplitude is 8 divided by 2, which we talked about. So we know that's 4 times 10 to the minus 2. Multiply by omega. Well, omega is 2 pi f, and we know f is 4.5 hertz. So 2 pi times 4.5 is 9 pi, which is 28.3 radians per second. So you get, these are where you get the marks for. Okay, I don't think you get a mark for the 0.22 seconds here. You get it from putting the 0.22 seconds on your graph. Okay, so once you do that, you've worked out the omega, you get a mark for that, and then you can work out that V equals A omega, maximum value. Okay, now I'm saying at the beginning it's starting as a negative because it will be in minus. Yeah, at times 0 it will be, this will be, is that right? Or is there going to be positives? Anyway, I think it doesn't really matter. So I may have got a mistake in terms of plotting the other way around. So Vmax is the amplitude, which was worked out here. multiplied by the omega, which we worked out here. So the maximum velocity at either end of the swing will be 1.13. Okay? It doesn't tell you where to start the graph from. So as long as you've got these values on there, the maximum value and the minimum value, you will be able to get that mark and the 6th mark for working it out. The sinusoidal, you need to show at least one complete wave. Once you do that, you have to determine the acceleration. So that's almost the other equation which we haven't used yet, but I've shown it to you before. So you put omega squared in there. So omega squared, the minus just shows that the acceleration is in the opposite direction to the displacement, multiplied by the maximum amplitude, because they want maximum acceleration. That means when x equals a. Okay, so you know that value from before, and then you multiply the numbers together, you get 32.0 point something else. But again, you round it up, and it comes to you the correct answer. And then finally, they ask you to suggest why particles of paint in the can will experience a maximum acceleration that's different from this. Well, the can is the physical object that's being shaken. Inside the can, the particles are all free to do what they normally do, and some of them may be moving randomly, colliding with each other or whatever. So any reasonable answer you can give, let's have a look and see what they accept as reasonable answers. Okay. Question 19b. Here are the reasonable answers for question 19b. So 19b says that so here are the options they give you. Particles are free to move inside the can. So, and then these are any of those answers. So I don't know which one I would have put. Hopefully I would get a mark. You can read through that in your own time and see if it makes sense to you. Okay? So first one says, not all particles will move with simple harmonic motion. The amplitude, frequency, the period of the oscillations is different to the amplitude of the can. But they're basically not connected, so there will be a difference in the motion of the free particles inside. Okay? So they said this one's good. The particle may continue to move upwards as the can starts moving downwards. Particles may collide with each other. Force on the plane particles is not equal to the force on the can. So anything reasonable gets you that 1 mark. Okay? And then we're on to question 20. Final question. Question 20 is about cesium-137, radioactive isotope. So cesium is often produced during the fission of uranium. So this is a common daughter particle. State what is meant by fission is when a large nucleus splits into 2 smaller nuclei. That's what I would put. A large nucleus splits into 2 smaller nuclei. They've accepted fragments. Okay? I wouldn't accept fragments. I would use the term nuclei. I would put 2. I wouldn't put or more. Okay? But this is what the mark scheme allows you to put. Of roughly equal mass, they're saying. It's in brackets, so it means you don't have to say that. And then some extra neutrons plus extra neutrons. But fission is actually when a large nucleus splits into 2 smaller nuclei and therefore releases energy by making something more energy efficient nuclear-wise. So cesium-137 decays by beta radiation. So here cesium gives off beta and then produces barium. So I've put the numbers in. The bottom numbers must add up. 55, 56, minus 1, so 55 on both sides. The anti-neutrino has 0 for mass, 0 for charge. And then to the top numbers is 137. All the nucleons stay in the barium. What's happened is one of the neutrons has changed into the protons. So a neutron splits into a proton plus a beta minus plus to balance the energy out, to conserve the energy in the antineutrino, and it will be an electron neutrino. So explain why the emission of an antineutrino in the decay leads to a range of energies for the beta particles. Okay, well, I don't really like the way they've worded this question. So what they're asking for is explain why this process produces a range of energies for the beta particles. Okay? And this is how they discovered that there must be neutrinos produced. So when they worked out the missing energy, so they obviously this this conversion, basically a neutron splits into a proton and an electron and gives off some other particle, which this is where they discovered it. When they worked out how much energy this should be using the delta M value and c squared, the amount of energy they got for the kinetic energy of the beta particles was a distribution of all sorts of energies. Now the maximum energy mathematically, I think, is about 0.78 or 0.782 mega electron volts. So this is how much energy is released when a neutron splits into a proton and an electron. So the way they worded it, I think, is wrong. So I would have said, explain why this decay leads to a range of energies of the beta particles. I wouldn't have put why the emission. It's not the emission of the antineutrino which is the cause. It is the solution to why the beta particles didn't all come out with the same energies. When you do an alpha decay, which I think we did earlier, all the alpha particles come up with the kinetic energy, the same kinetic energy. With the beta decay, they don't all come up with the same kinetic energy. So say the beta particle, the most common statistically, the distribution of the particle energies, the frequency of how often they had which energy. So the most common energy that they came out with was this much. So this is how much kinetic energy a typical beta particle would get. So that where's the rest of this energy gone? Between there and the maximum value, which is here. And the rest of that energy went to the neutrino. And that's how they realized there was something missing by the conservation of mass. So anyway, this is the explanation of the underlying discovery of the neutrino. Energy released in this decay by E equals mc squared is constant and shared between the beta minus particle and the newly discovered neutrino and something else. That's what they should have said. So not all the kinetic energy goes to the beta minus. It is shared randomly between the two particles. So the beta minus particle and the neutrino take some of the kinetic energy that's available to them. But they haven't put this second part in there. They've put something ridiculous like, as the beta minus is ejected from the nucleus recoils. Well, that's got nothing to do with why the emission of a neutrino leads to the range of energies. So anyway, the marks they're giving you for are that, and I think they're wrong. They should have given you what I'm saying. Anyway, I'm trying to explain it to you, and I think the chief examiner on this occasion has got it wrong. Okay? Okay, so that is part B, and this is a long question. It's 14 marks. Question C. Okay, so it's saying cesium-137 is a major waste source of radiation from radioactive waste. Why? Because radioactive waste is in a nuclear fission reactor. Yeah? And nuclear fission reactors are going to produce tons of waste, or kilograms, not tons. Because remember, a little bit of nuclear fuel goes a long way. A nuclear fission reaction produces about 24 kilograms of cesium-137, which is going to be nuclear waste. Okay, so that's mass, 24 kilograms, big M. A website states that 24 kilograms of cesium-137 has the same activity being given by this equation. I don't think you need the minus in there, according to your equation sheet. Okay, but it's just to show that the activity is decreasing with time, but you don't need it in there probably. A website states that this 24 kilograms has the same activity as 2,000 kilograms of radium-226. Okay, and then here they're giving you the activity of 2,000 kilograms of radium here. So now what you've got to do is to work out what is the activity of 24 kilograms of cesium-137. Okay, well the half-life of cesium is 32.2 years. They're giving you that. That means T half-life is that many seconds, because they've told us 1 year is that many seconds. So you've got to change the years into seconds. So again, they're giving you this number. So that's something for you to remember. They don't give it to you in a data sheet. They're giving it to you in the question. So it looks like this is a common thing that comes up in this exam. So once you get that value in seconds, I haven't done it, probably because I didn't have a calculator when I did it. So once you do that, here it is. It's in full, the time here. Once you do that, it allows you to work out the lambda, the decay constant, okay? Because we need the lambda there. So we know that the mass of one cesium has 136 units, and we know 1 unit, yeah, 1U is equal to this value in kilograms, 1 atomic mass unit. So the mass of cesium is 1 cesium atom in kilograms is that. And we got 24 kilograms of it, so we can work out how many atoms of cesium we have in 24 kilograms. Divide this by the mass of 1, and you get how many atoms there are. So in 24 kilograms, you got 1.06 times 10 to the 26 atoms. Okay? Now, we know half-life can be calculated in seconds. We've got a natural log of 2 is always 0.693. You can try that on your calculator if you didn't remember that. You can then work out the decay constant. Once we've got a decay constant, we can use mathematically A equals lambda n. As I said, you don't have to have the minus sign in there to work out the activity at that time. So once you know you've got this many atoms, and you know that the probability of decay is that's going to be your number of your activity of source in becquerels. So that compares to 7.33. 7.73 is slightly greater than the activity of the 2,000 kilograms. So the question said, a website says that 24 kilogram has the same activity. Well, it's almost the same. It's slightly greater. So I put it slightly greater than the activity of 2,000 kilograms given above, which is this value. So 7.7 is roughly the same. So I put it that way to basically hedge my bets. It's slightly greater, but it's roughly the same. So I would say it's pretty much whether the statement is correct. It's roughly correct. Okay? They can't penalize me for saying it that way. So that's the second part of the second page of question 20. And here's the final page of your exam. Cesium-137 may enter plants grown in a contaminated area. In other words, if the area is contaminated, it means some of the cesium has got into the soil and the plants take it in. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels, that's 100 grams. Count rate of 150 is considered safe. Okay, so we've got 100 grams of plant material. Initially, when you cut your plant down, it will have got 500 becquerels potentially, which is greater than the safe rate. So if you've got 100 grams of plant material, you're exceeding the safety limit. Determine the time taken for the count rate from 25 grams rather than 100 grams. That's a quarter of the material grown when it gets to safe level. So 25 grams is a quarter of 100. So the activity initially, activity 0, will be 125 becquerels. Okay? So how long will it take for it to reach 125 becquerels? Okay? So the activity initially will be 125 becquerels, A0, and safety will be when 150, this is becquerels is per second, so that's per second, and they've given us per minute. So we want to change that to per second. So 150 per second is divided by 60, 2.5 is a safe limit. So I was mistaken at first, this is per second and they've given it in minutes, so you can't compare it, but it's way more. So the safe limit would be 2.5, so that's like way bigger, 200 times bigger. So when will it reach 2.5 becquerels? Well, we have to use this equation, A equals A0, e to the minus lambda t. So we know lambda from the previous question. We worked out lambda here. There's our lambda, so we're using it from the previous question. So 2.5 is A. 125 was our A0, yes, because remember we're talking about 25 grams of that. And e to the minus lambda, and t is the unknown, okay? So you can put the 2.5 and the 125 on the same side. So when you take logs, you're taking log of just the fraction. So when you do that, log of 2.5 over 125 will become, taking logs here, basically eliminates the value e, is that will be equal to whatever that log is. And that log is minus 3.91. So the minuses cancel out. So that is minus 3.91. So changing the subject to the equation, you get 3.91 divided by 7.29 with a factor 10 to the minus 10 gives you a value of that. And again, we know that we can convert it into years if necessary. But in the exam, they have accepted it in seconds. So you can Oh, they put it seconds, but then they put 171 years. I got 170 years. I think they used, by mistake, they put in a value here of 7.28. I think that should be 7.29 times 10 to the minus 10 from our answer before. Here, you see? I think they just had a typo error in their calculator. So that is the end of this paper. I hope you found it useful. Once again, remember to like, share and subscribe so you know when the next video is ready. Unit 5 and Unit 2 will be my main targets for this term, because obviously Unit 2 is the main content for Year 12 and Unit 5 is the main content for Year 13 this time of the year. Okay, well, thank you very much for watching and hopefully see you in the next video.